So I'm going to talk about in this lecture, let's see, how do I do this? Okay, good. So today I'm going to talk about 4 papers. So first is DETr, and this is the still image-based paper applying application of transformer for object detection. And this was actually one of the earliest paper, even before the ViViT and so on. Then we will get into video. We'll talk about 2 papers. One is the TimeS transformer. Second one is the ViViT VI video, because we heard the ViT, the video transfer, the vision transformer, or the image transformer, visual image transformer, and this is video. So they come up with very interesting acronym for that. And then few points from this survey paper we have to conclude the discussion. As I said, that we have a very nice survey paper on the transformer, which is getting a lot of attention. So if you want to know a lot of work, so that's another venue you can read and try to learn. So let's start with this thing. This is DETr. This is called detection transformer, and this was published in ECCV 2020, and it is called end-to-end object detection with transformers. Okay, so you guys have learned in 5415 the object detection method like Foster series or CNN. So that has a couple of components. So one is that it's a region proposal networks. You find the potential areas in the image where object can be. Then there is classification of those, and then you kind of come up with the adjustment of these proposals, the bounding boxes to get a tight bounding box and so on. So there are several steps to that. So of course that was based on CNN. So here they want to use transformer, and it is actually predicting a set of prediction. We'll show you. So it's very streamlined pipeline. So it removes these different stages as we have in Foster or CNN. And so it will detect, it will output the set of prediction parallel, all the objects which are present in the image, and it will have these learned object queries, and we'll show you how this works. So it performed pretty well on par with Foster or CNN on COCO dataset. And it can be generalized also for panoptic segmentation. So, one is the semantic segmentation, where you assign each pixel label, what kind of category it is, and then object detection, which, put a bounding box, which object is, but then you combine those two. That's called panoptic segmentation. You'll have both. So this is the high level idea. So we have here image, and you compute CNN features, which are here, and then you do the transformer encoder decoder, and the output will be the set of bounding boxes. And these bounding boxes each will represent an object. And so what we are going to do is, this is our ground truth, and this is output from the network. And then we are going to, in order to find the loss, we are going to match these, the detection from the network with the ground truth. And so there are this will be called bipartite graph. So the one partition is this one, the detection from the network, and one second partition is from the ground truth. So we are going to find out that while the detector gave us that there is object here, and then there's another object here, and there's another object here. Now ground truth is this, so we need to know that this detector object, whether it belongs to this one, if it matches with this, or matches with yellow one, and similarly for this. So this matching will be done using bipartite matching, and there's a pretty famous algorithm called Hungarian algorithm. It's very standard to use that. So a little bit more detail. So we take a image, get a CNN features, we do the position coding, we get these tokens, the transform encoder, we get encoded tokens, and then we have decoder, and then there are object queries. So these object queries, they say they put 100, so maximum number of objects can occur in an image is 100. Okay, so then they go through the decoder, and the input to the decoder is also from the encoder. Then it outputs is 100, and then each one is potentially the object. So then we get this, and we are fully connected, and we give you what class of object it is and what is the bounding box, and this can be like that. So a little bit more detail. So we have image features, and these are value, key, and query, multi-head attention, and all those things, normalization, skip connection, fully, and all this. We haven't talked about that. And of course, you repeat this n times. And then we have the decoder. Then this is the object queries. Okay, so this is pretty very interesting, innovative way to solve this object prediction problem, that we will learn these, we'll initialize these randomly, but then we'll learn. So the idea is that for each one, we will find out, will give us that output will be same number out here, as I showed you earlier. And then that will be basically object. And we will estimate a class in the 4 numbers, the bounding box, the center, width, and height. And as you see, there's attention, the position coding, and also position coding. Now here, we will have the output coming from encoder, which will go to decoder, and that's the way it works. And this is a standard transformer, as we have been talking about. So now the important concepts here is these bipartite matching. So what this data is going to do, it will output the number of objects, bounding boxes, and their classes. So this is a ground truth. So we say the object, this one is first object type A, this is a bounding box, and second object is object type A, bounding box, and so on. We'll have these one. This is a ground truth. We know that for a given image. And this will be the output from the detector. Again, the same idea. Now we will have the maximum number of the objects, which can upper 100. So if there is, less, so we'll just have the null, the phi, and that's fine. So the main thing here is that we will have a node in this graph for each of the ground truth object and each of the detector object. So the idea is that while network gave us this, we want to say, well, this matches with which ground truth object. Because typically you will have just one object in the ground truth and one object in the detector. Or if you look at the classification, single classifications, single class. So you'll have image, you say it's a dog, or there's another image which is cat or airplane and so on. But here in an image, there can be several objects present. So we have to know that when we compute the loss, how good is our prediction? So which object from here should match with the ground truth object? So that's very important concept. And given these detection from the detector and given the ground truth, so we are going to find the base match. and that match will depend on the cost, how similar these are. Of course, the class has to be same, and then bounding box should be similar at the overlap. And to solve this, we'll use Hungarian method. Okay, so Y we will call a ground truth set of objects, and then Y hat is the prediction. These are coming from the detector, so they are n of those. Then now, in order to match the ground truth object with the detector, we are going to use these two things. So one is that this is a bounding box from the ground truth, and this is a bounding box from the output of detector. So we want to look at how similar these bounding boxes are. And of course, the class has to be null, has not to be null. It has to be some class, one of the class from COCO. And this give you a probability that what's the probability that this particular detection is of this class. So that's what we have lost. So this is the distance, and this is the confidence probability, and that's why we have minus. So we want to minimize this loss. Okay, the match. So then each ground truth, we have the class of that object and the bounding box. So 5 number. Okay, so now we want to find out the given these detections, there are many different possible ways that these can match with the ground truth, right? So even if you have two objects, two objects from the prediction and 2 objects from the ground truth, now this can potentially match with this one or this one, and this can match with this one and this one. So there are several possibilities. So each one will have a cost. So we want to come up with the one which give you the minimum cost, and that will be the index here. So we want to come up with the sigma hat, which will minimize this cost for all these matches. And this is a prediction probability. So then the total loss will be the one is the, we want to maximize the probability of class, or we want to minimize the minus of that, which is fine. And then we want to get a closer bounding box to the ground truth. So this will depend on the intersection or union between the ground truth bounding box and the detection, detector output bounding box, which matches the batch, and then it's L1 distance between bounding box. So that's the way this method works. It's a very nice slide from this guy. So I just used that one with the credit. Okay, so this works pretty well. As you see on COCO, they get very good results. This is the different versions of that, the 44.9. And then they compare with FOSSA or CNN, and these are the different details, parameters, and parameters not that high, as 60 million parameters. So, and then this can be used also for panoptic segmentation. So, which means given an image here, you want to come up with like this. Okay, so every pixel will have a class. So they build upon the DETr, which will give you the bounding boxes. And then these are the bounding boxes here. They will put the multi-head attention. So you'll get these attentions, and then they will concatenate, and this is just upscaling. So you'll upscale once, twice, and 3 times. It's called feature pyramid network, and you will get these. And then you, for each pixel, you'll do the argmax, whichever pixel has the highest probability of that class, because there are different classes, with a tree, or sky, a cow, or grass, and you output that. And they have pretty good results. And this follows similar to the mask or CNN. Mask or CNN takes these FOSSA or CNN and get you the segmentation. So, and you can get results like that. So it's pretty nice results, segmentation. Okay, so this was the DETr detection transformer. Of course, I mean, this paper has a lot of details. So we will spend a whole lecture, one class on this, but this is a general overview of that. And this paper is, cited quite many times, 1400 times. So this was a good, I think the first paper on the use of transformer in computer vision, I think, even before ViT. Okay, so now we will get into video. Video, as you know, is a sequence of images. Instead of one image, we will have lots of images, and typically you will have 30 images in a second. This is a paper called Space-Time Attention, All You Need for Video Understanding. So it's, following similar title like Attention's All You Need, the first paper which started this whole thing. And this was published in ICML. So yes, let's look at what this is about. So now what we want to do, we want to use a transformer for the video. So I was talking to Sarat, the student who's taking this class, he's here, that I think that's more important that you guys understand the basic concepts and come up with new ways to solve the same problem. And what is happening that, this original transformer paper, as you remember, it was NeurIPS 2016. So it was used a lot in NLP, but it took several years that people actually adapted to vision. And now it is kind of race going on that, well, okay, since the transformer is very popular, so what problem you can apply transformer and show? First is that you are showing that transformer works for this problem. Second, of course, is that you have to show that it works better, performance better. So now in all these deep learning solutions, there are these few important things you have to keep in mind. So one most important thing is the performance. Any problem you solve, you'd apply on benchmark data set. More data set you apply, better it is. And your method has to give better results than all known methods. If it's not the case, it's very difficult to get paper accepted. That's a minimum thing. Then second thing, of course, you have to have novelty. And third is that, well, in these kind of transformers, that what data set are you, for training, are you assuming very large data set, which is unrealistic, it's not public and so on. And also how fast it is and so on. So those are kind of things are there, but they are secondary. The main thing is that, if you are the first one to apply transformer the video, then you will get a credit. And then if you show that, the results are better than CNN, other known methods, then you'll get on the top of it another credit and so on. So anyway, so this way, okay. So these are the guys, they started, they use this transformer to video, and basically they adapted ViT, which we have discussed before, from images to video. And so now when you go to video, as we've been saying, the main big thing in transformer is attention. And attention is between tokens, and we talk about attention and pixel-wise attention. A lot of computation not possible, so we have taken image to do in pages and all that thing. That's what ViT does. And depending on how big is a page, if the page is small, there'll be too many pages, attention will be large, and all those issues. So now when you go to video, it's even become more complicated because you have several frames. So how do you do it? And these guys actually, explore several ways to do it, and they come up with what is called divided attention, and works pretty well. and applies the attention separately, temporal and separately to spatial. So it gives state award results on several benchmarks, including Connective 400, Connective 600, and compared to 3D convolution, it's faster to train, and it can achieve dramatically higher test efficiency. Okay, so these are the data set for action recognition. And there's a build-up after UCA 101. They came up with this thing. So now this is a larger data set than UCA 101. Okay, so now self-attention schemes. So let's say in a video clip, you have 3 frames. And now what are different ways you can do this attention? So first is we divide each frame in these batches and each become a token. So this is space attention. So you just have attention of this token only spatially. Okay, so all the tokens in the same frame. You don't look at other frames. So that's called spatial attention, space attention. So another possibility is spatial temporal attention, space-time attention. So for this token, you will get attention from all these tokens in 3 frames, and there'll be a lot of computation. Then other is divided space-time attention. So this token will get the space attention from that frame, and then temporally it will get from same token in this frame and this frame, same location. So this is very similar to what is called R2 plus 1D convolution. Okay, so this one is sparse global, local global attention. So what you do for this token, you will get a space attention like this, but it is the 3 by 3, not the whole thing. So 3 by 3 here, 3 by 3 here, and so on. So that's why it's local, but you do temporally all these. And then this one, we have axial attention. So what you do here, you do the time, the same location of this token. So from this frame, and then spatially you do the X and the Y. So that's why time, width, and height, axial attention. So and then they have this nice way to explain this. So what's happening here, you take from previous layer, you do space attention, MLP, and Z, that's a standard thing, like here. Then this one, join the space-time attention, which is you do previous layer, join space-time at MLP again. So you can take all of these here. And this one is divided space-time attention. So you first do the time, then you do space and MLP. And here we have a sparse local global attention. So you do local attention and then global attention, and then you do the MLP. And the final, this one, axial attention, as you see here, first you do time, so this way, and then you do the width, okay, and then you do the height, like this one. So then they find out that, these are the different ways to do it, and they get pretty good attention, pretty good performance for Connective 400 and something version 2. This is another data set. They get 78% here, 59%. And these are the different parameters for these different networks. And they compare with these other CNN, and they get improvement, 3% from here, 2% here, and they also compare the parameters. As you see in the time, it doesn't take that long. Time-wise is good, and flaps computation is smaller, and also the parameters are more compared to other ones. So that's one thing. Okay, so that was the TimeS transformer. And then the next one is ViViT, ViViT. So this was published in ICCV last year in October. So it's couple of months old. Already have 124 citations. So this one also deals with these special temper tokens because they want to, apply this to video, and then they also, evaluate different ways to do this, attention, because you have space and time, and then they pre-train on ImageNet 21K and JFD, and it achieved state-of-the-art results on multiple benchmarks like Kinetics 400, 600, Epic Kitchen, something, and moments in time. So given the clip, the 3 frames, you get these pages and you get these position coding and so on. This is like a standard, your transformer thing, and your MLP head. So they look at, these about 4 different models. How do you do the attention? So one is spatial temporal attention. And so you take these images and divide in patches, you get sequence of patches. And this is basically similar to what is called what we just learned earlier, joint space-time attention. Okay, so model 2, the factorize encoder. So here, what they are doing, they do first spatial transform encoding each frame separately, like here. Then after that, you do temporal transform, and this is their figure: spatial, then temporal. Then they have model 3. So here they are doing the spatial self-attention block, and then they do temporal self-attention. So that's model 3, and which is shown here, spatial temporal, different blocks. Finally, the model 4, which is a spatial temporal together. And so for each token, you compute separately or space and temporal dimension, and they have different heights for that. So they look at all this, and I thought there were some, maybe I had, and let me check these were performance were there. Okay, yeah, sorry. I hid this one. Okay, do it again. Okay, you guys can see it again. So these are the results. So the Connected 400, Epic Kitchen, and the runtime parameters and so on. And they get, for this one, they get the best results. And then this one also. There was another slide also. Let me check 1 second. Maybe this one. Maybe I just remove it or something. Okay, yeah. Anyway, so that's in the paper. You can look at that. Okay, so so that's the very general description of this this paper, the ViViT, which we are going to discuss also in the class. So then I want to end just talking about the main points in this, what we have discussed so far. So these are taken from our survey paper, which is also a very nice way to learn what have been done in vision, because the field is moving so fast. There are lots of papers. And this accepted, in the SEM computing survey. We already have quite a few citations. Okay, so the important thing is that what are these different design choices when you do the applied transformer? So you're going to go through what problem or task you are solving. what's the method and what are the different, different highlights, and what's input data, what's label type, what's loss. So as we talk about, first one is ViT. So it's basically adapting NLP transformer encoder for images, and they get the patches, they get embedding of these patches, and then do the position coding. Pretty simple, straightforward. And they are applying 2D images, and their class labels and losses cross entropy. Okay. So then we talk about the data efficient transformer. So there the main thing was that there was a student and the teacher. So they use a distillation. So teacher model is CNN and student is the transformer. And this knowledge distillation actually, made a big difference. And again, this input is 2D images, class label. Now here, beside cross entropy, you have this scale divergence for the distillation loss. So then there's a clip, which is very popular also. We haven't discussed that so far, but we will discuss in this separate lecture for this. One day we'll discuss that paper, and that works with images and text. So that's very interesting. It can be used for zero-shot learning. So it's trained jointly on image and text encoder. So we have image, we have some, say, captions or some description, and then we want to come up with the image text pairs label type. That's the way it's learned. So then we talk about DETr, which is the object detection problem. All these are like image classification. This is object detection. So we do the linear projection layer to produce CNN, and then we have a special embedding, and then object queries, which actually go through a decoder and get input from encoder and get you the output of the potential objects which are present in the image, and there's a parallel output, there's a set. And it operates on 2D images, class label, and as we just discussed, Hungarian loss based on bipartite matching. So then there's another paper, and we will discuss this also, which is a deformable DETr. So that works for the smaller object, and it's a multi-scale attention, and also 2D images and label type class labels and Hungarian loss. Now, other point is to look at the, the advantages and limitation of different transformer-based methods. So if you look at the task image classification, so this was the first one, and the metric was used top 1 accuracy ImageNet, and we got 88.5. Now this was the first one, application of transformer, global self-attention directly on the image patches. It's convolution free and outperforms CNN models such as ResNet. But the limitation was it was trained on the JFT, 300 million images. So that was one problem, and other was, of course, that it has large model, 632 million parameters to get the SOTA state award results. Then the DET get you a little less, 83.1, also on ImageNet, but this is used, training is on ImageNet, doesn't need very large data set, 300 million. And it is the distillation is a new thing here, which really helps. And it computes pretty competitive performance with small model, 86 million parameters compared to 632 here. Of course, it requires the teacher model from CNN, so that's kind of a limitation. Then we talk about SWIN, which called the Moore prize, that give you, better than DET. And so the main thing was a hierarchical design, because they were doing these windows and then shifted windows, and they were changing 4x4, then 8x8 and 16x16, so hard to train and computation complexity is more. So then we talk about DETr. It's the metric is average position. It's object detection task, not the classification. The data sets COCO and get you this performance. And this is interesting that, just end-to-end object detection, and we don't have these other steps as faster RCN and like region proposals, network, and so on. But doesn't perform good on the small objects and require long training time. Then there's a DETr, deformal deter. So achieve better performance on small objects and get a good average position. So then one can also compare this transformer model with CNN models, So these are in the papers, a lot of detail. So as you have been talking about, that one is parameters, how many parameters you have. Other is, computation. And then third is the performance. So as you have models which are heavy, then the performance will, improve, of course. And so these are the different things that you see on the MageNet. You can go up to, 88 or 84. So this kind of give you some idea comparison with the CNN and so on.